Up next, we have Andre Lima, who's going to take us into hardcore red team technical deep dive into the Windows kernel, rootkits and whatnot. Andre is at PwC, and he is a new to Norway person in the security community. So we're very happy to have him here.
Thank you.
Let's hear it for Andre. Take it away.
Thank you, everyone. So today I'm going to talk about life in the Windows kernel for red teams. My name is Andre Lima. I recently moved to Norway from Australia, and I'm working at PwC Norway, and I usually am doing pen testing and red teaming. But what I really love to do is research, and I will often publish on my blog. And that YouTube thing is just, I was playing with video editing at some point, and I decided to just do some YouTube videos. And at the same time, I was studying format strings, which is exploit development. And I decided to do a very thorough series on it. So if you want to check it, that's the link. And yeah, if you have questions, obviously, just ask afterwards. If you don't have time, you can easily reach me at Twitter or LinkedIn. So this is what we're going through today. I don't have much time, so let's just jump into it. Just some clarification, though. This is not about kernel exploitation. Usually, those types of talks will end up in, oh, now we get code execution in the kernel, and you can do pretty much everything. That's very vague, so today we're going to see what's everything. So should I care about this? Should you care about this? Obviously, the answer for me is yes, but the question you have to make yourself is, if you're a new blue team, blue team in your company, you obviously have bigger fish to fry, kind of thing, like bigger priorities. This would probably be stuff that you will see more often on some sort of nation-state attacks, where the technicality goes really deep, and you would often see rootkits. And I just did some quick Googling, and I found some of the ways that you can actually get code execution in the kernel. In this case, having a properly signed rootkit, which is also the example of Mimi Drive, for example, from Mimikat's repository. And the other way is for you to find the actually legitimate driver, have it installed and loaded, which will be allowed by the operating system because it's legit and it's signed, and by a known CA. And you find a bug in it, and you're able to exploit it, and then you execute code and load your own driver. But that's not the focus here, but it's definitely something, and more recently as well at Blue Hat conference, there was someone talking about the return of the kernel rootkit malware on Windows 10. So it's actually relevant, and if you're feeling very confident as a blue team, then it's definitely something you should look into. Now, the other day, someone asked me what was I doing at BSides, what I was going to talk about, and I just started talking about the kernel, and all of a sudden I realized that not everyone knows what's the kernel, so I decided to put this in and just to make a quick intro. This is a great oversimplification, but basically the kernel is the part on the operating system that will take care of all the stuff that you don't really want to care about, like scheduling and resource management, how much memory you have, are you efficient in the use of memory and whatnot, blah, blah, paging and such. So usually in the user mode, you will interact with the operating system by calling some sort of API function, and that API function will reside in a DLL, usually inside a subsystem, such as Win32. And it will trickle down to the native DLL, NTDLL in yellow. Then what happens there is eventually a syscall instruction will get called, and that will trigger the transition into kernel mode. And one of the most important parts in the kernel is the executive there in purple, which includes mostly the various managers. So object manager, process manager, security manager, input-output manager, there's a lot of managers. And then you also have the kernel there in dark blue. It looks like black, but it's also known as the lower kernel. And that's basically responsible for scheduling, interrupt, and exception dispatching, and implementation of various kernel primitives, such as mutex or semaphores. It gets a lot more complicated, but for the purpose of this presentation, that's pretty much what you need to know. So let's go through an easy methodology on developing rootkits. So the way you usually go about it, obviously it can be different, but you will try to understand the feature you wish to manipulate or use, and then test that manipulation live on WinDebugger, if that's possible, or easier. Then write the code to replicate the test, compile, crash, and restore a snapshot, and repeat. But the crash usually in the kernel usually translates into a blue screen, and you don't want to be wasting time just restarting the VM. So what you would usually do is take a snapshot of the VM right before you actually do whatever you want to do, and you then just restore it, and that's a very common thing when you're doing that. Let's look at an example of removing process-protected light. So PPL. WinInit is one of the processes that is a PPL, and as you can see when I open Process Explorer, if I try to get the DLL window opened, you will not see anything. Obviously, it has DLLs, but the whole point of being a PPL is that you cannot attach to the process, you cannot read the DLLs, inspect its memory, analyze it, and so on. So it's kind of isolated. Its virtual memory is isolated from the other processes, no matter what the privileges you have on the machine. Now, if I grab that process ID 548 and I put it in the WinDebugger, I will get the executive process structure memory address. That's, again, a process manager inside the executive that I just mentioned. And when you, I'll just refer to that address by what ends 8080. So now that I have that, I can look into and tell Debugger, so this is an executive process structure, and this is the address in memory it is. It will parse it and give you all the data because it already knows the structures. And then at the bottom, at offset 87A, you will get the PS protection, which is 87A, and next is 87B, so it's exactly 1 byte. And what it is it has value 61 in it. That 1 basically means that's you being processed a protected light. Now, if I edit that byte on WinDebugger to 0, then all of a sudden, as you can see on Process Explorer, I can now see all the DLLs and inspect into its memory because it's no longer a PPL. Now, all I have to do is write the code, and off we go. Now, why am I saying this is easy? Well, the reason it's easy is because the reverse engineering has been done by one of the best in the business, Alex Ionesco. You just need to read the blog and understand the features really well and all the structures that it implies, and just realize, oh, I just have to go there and edit that byte and put it 0. Then I have to, the code is already written by Gentle Kiwi, who created and maintains Mimikatz and the associated projects, like in this case, MimiDrive and MimiLib. So this one is kind of easy to implement. Let's look at something a bit more complicated. So let's try and hide a process. In this case, oversimplifying it, this is basically a matter of you going through a doubly linked list and rearranging the pointers and basically making that node that you want to make disappear. And that's it. However, it's obviously a lot more complicated, and I'm going to try and explain why. So, in order to understand how tricky it gets, and all the synchronization mechanisms here required that are quite odd, you need to understand what RCLs and DPCs are. So RCLs are interrupt request levels, and DPCs are deferred procedure calls. So for you to understand Urkels, let's talk about preemption. So preemption basically means it's a scheduling algorithm, and it basically states that you being the thread in the process, you have a limited amount of time to execute. Then what happens is, in the middle of your execution, the CPU is taken away from you. How exactly does that happen? Well, an interrupt goes at dispatch level, which is level 2, and you will get, so code at that level will run, and the code running there is called the dispatcher. The dispatcher will assign a new thread, just put back all its memory, put back all the registers it had in place, and just resume the thread. And so the point here that I want to make is, if you're at dispatch level, the CPU core, the logic CPU where you're running at, cannot be taken away from you. Because if you're at dispatch level already and an interrupt comes at the same level, it doesn't get triggered, so it will be pending. Only interrupts higher than you will get executed. So we'll take the CPU away from you. Now, why DPCs? You can think of DPCs as basically callback functions. Now, to understand that, I'm going to give you a basic example. For example, imagine you have, by the way, the device circle is basically a range of values that can go up to high level. Now, imagine you have a device like a network, and you receive a packet, and that device then sets a trigger. Let's say was assigned Urkel level 12. So you're at Urkel level 12, and you jump up there to do whatever processing you need to do and grab that packet. But at the same time, you have a webcam because you're in a conference call. And that one, the webcam is assigned, that device is assigned Urkel 10. So because you're executing here at 12, that 10 will trigger, but it will be pending. And if you take too long up here, you will basically have like a frozen image kind of thing, and what's wrong with my camera? This is because it violates one of the basic principles, which is you should never take too long at any interrupt. So, but what if I have a lot to do? So that's where the DPC callbacks will come in. What usually happens is you will have that network device will do whatever it needs to do as quickly as possible, and then set a DPC which will run at dispatch level and jump back down. But because there's this 10 pending, level 10 pending the webcam, this will get executed. And this allows all this thing to run a lot more smoothly. And that's the purpose of DPCs. And this is important to understand so that you can understand then the algorithm. The first thing you want to do if you want to change that doubly linked list is raise your Urkel. And the reason you're raising your Urkel as a thread is because you do not want to be preempted. So I got that synchronization problem solved, but only on my CPU, on the CPU core that I'm running at. The problem is there's probably a lot others these days that are running, and I want to control them as well, because if I'm moving around pointers on that doubly linked list, and some other process goes through the list and it's in an inconsistent state, that's an issue, and that's going to be a bug every day. Blue screen every day. So what I want to do is make sure that everyone is also not doing anything. So what I do here is I have to use, part one, Spinlocks. Spinlocks is a synchronization mechanism, and by the way, the reason I cannot use mutexes, semaphores, and whatever other typical synchronization mechanisms that you're used to, is because they all run at passive level, as in which, by the way, user mode also all runs at passive level, and When you get into that protected area that the synchronization mechanism is protecting, you usually have like some sort of entry function and some sort of leave exit function. When you hit that entry, you usually suspend your thread and allowing the dispatcher to assign something else happen until you get triggered again because the condition, whatever it is, to protect that region is satisfied so you can get into. However, suspending the thread, as I mentioned before, at dispatch level will not run. So if you try to use those normal synchronization mechanisms, you're basically giving up CPU and no one will catch it back, basically. And there are watchdogs on Windows that when they realize that is happening for too long, they will blue screen you as well. So that's the reason why you want to use Spinlocks. Spinlocks is a synchronization mechanism that is pretty much, think of it as an infinite loop. It's obviously not infinite because it will check for memory position on an object and check if the condition is already done. But it doesn't give up the CPU. It just stays there cycling on that condition. So that's why you need Spinlocks. However, this is not enough to, by the way, the way you execute, you make sure the other CPU cores are running the Spinlock is, going back to this slide, you have that number entry, a DPC structure. You can set it to a specific, the index of the CPU cores you have. So if I want the first one, that's usually index 0, I will assign that number to the DPC and make sure that that DPC is attributed to that specific core. Now, just using Spinlocks is not enough because there's an issue here, which is usually synchronization mechanisms will protect a specific area. Now, my problem here is that there's no real area for me to protect because it's code that they could be accessing the resource on another part of the operating system that I simply don't control. So my problem is the CPU core could be anywhere around the system and just decide to go through the process list, and that's the part I'm trying to avoid. So I wanted to make sure that it's actually there, the Spinlock. So I'm forced to use also a counter. So if the virtual machine has, let's say, 4 CPU cores, I'm running obviously on 1, so I'm expanding that counter to reach 3. I'll put that increment right before it getting into the Spinlock. So when I see that the counter has reached 3, I will then assume, okay, I'm good to go. I can now manipulate this doubly linked list. And that's pretty much how you do it. The original idea was from Greg Hoagland and Jamie Butler. It's not as straightforward as just using the code they have on the book, because obviously it's more modern system, so you have to adapt to it. Things like, for example, you used to have a global variable in the kernel that would give you the number of CPU cores that the operating system is using, but these days you have features like hot adding of CPU. So if an operating system needs an extra CPU, you can assign it to it, and there you go. That pointer, that value will therefore not be usable. So just some interesting things here. There is a remove entry list. By the way, after the acquire lock, which is this whole thing, assigning DPCs and with the spin locks and everything and the counters, you then go into the sensitive function. The only reason I wrote it this way is just to make it as flexible as possible, template-like, and I don't have to repeat the code every time I want something sensitive to run. So if I want to, I realize that there is a remove entry list. So why did I not use it on as a sensitive function? Well, the reason is it doesn't have those last 2 lines of code, which are very important. If you're rearranging the pointers, a typical thing, if you want to delete, let's say I'm the entry and I have a pointer back to the previous entry and a pointer to the after entry. When all you have to do is reassign the pointers from the previous and after so they can point to each other. And this one here it will not rearrange the pointer from the one that just got removed. So it will stay pointing to valid entries. The problem with that is that when you close the process and the operating system goes through removing that structure by itself, it will do some sanity checks. And one of those are checking if the one it's deleting, previous, after, is pointing at the entry that is being deleted, and if the after, previous is pointing at itself as well. Because I left them hanging and now they're pointing to each other, my previous after will point to my after. So that's an inconsistent, that's a blue screen. So that's why I need those two last line of codes basically to do this. Point to myself. And if you think about it, like the previous after, now it's me, so it's all good. And that way you won't crash the process that you're hiding after you remove it, which I'll show in the demo. Another interesting one is PS get process image file name, which you would see and you would assume, oh, this is perfect. Like one of the features of the rootkit is to remove a process based on its name. So you would assume this is just exactly what I want, to find that process, and then I'll have the reference to the process, I can remove it. The problem is, if you look into in Debugger, the actual structure that it returns you, it's 15 bytes long. So the process that is actually called search protocol host.exe actually just shows up as search protocol, which is terrible if I want to match it. But that's where reverse engineering comes into play, and you just look around for the information you want, and you write the code appropriately to access it. So if you look around in the same executive process structure, there's an entry called image file pointer, and on that image file pointer, there's an entry called file name, which gives you back a Unicode string where you will find the full name, and you just need to write code to actually retrieve just that part that is interesting to you. Another tip is, if you're trying to hide something, let's say like you have some sort of payload that you want to hide, but you don't want people to figure out. If you think about it, like if it's, let's imagine it's PowerShell.exe. So you should avoid doing that the most, just because the whole point of a rootkit is to be stealthy. So blue screens is not a good thing. Now, another bad thing is, if an admin is running PowerShell and looks into Task Manager and it doesn't see it there, that raises questions. So you don't want that type of thing. So if you have a payload, try to give it like a random password-like name that only you know, so that when you run it, it's good to hide. So let's just look at the first demo. Okay. We can make it, yeah. So I'm running a driver client, which is basically a user mode normal application. I wrote it in C++, could have done it in C#, but anyway. Wrote it in C++, and it has those features, and we're going to run through it now. So I'm loading the rootkit. Then I will call Notepad just so you to see normal behavior, and you'll see it in green showing up in Process Explorer. But then I will run hide by process ID, give the process ID, and you can see red disappears. Another one is hide process by name. And by the way, just to show that I can close the process and there's no blue screen. So the first option is hide by process name, and it's pretty much the same thing, and you'll see it showing up, and then I will hide it, and it will disappear. Now, Obviously, this is not like ideally stealthy, using stuff popping up and disappearing. But so one of the ways I did is I will hook to the actually create a callback function. So when the any process is created, I will try to match the name if it's the one I want to hide. And so that's why now I will configure it. Just close this. Now I'll configure it so that anytime it sees a process called notepad.exe being created, it doesn't even show it. So now when I run notepad, you will see that it doesn't even pop up in there, even though it's obviously running. Now the other one is hiding the driver name. So if you go to System and you look into the DLLs, it shows you all this, the modules upload, and you can see rootkit sys there. Obviously, I would have a more stealthy name, but then all of a sudden it just disappears. Another one is the fourth option, which is privilege escalation, just assign system privileges to a process. Now, so I'm trying to do something here that only elevated privilege user should be able to do, which is write to the root of the C drive. But so it doesn't work. I don't have enough permissions. Now I go down just to grab that process ID. That's 3460. And now I can do it. And that's it. Thank you. Let's now look at a keylogger. I'll try to oversimplify this. So the way it works, and this is a gross oversimplification, but is you will load a driver that will create device drivers. Let's just call them devices. There's different types of devices, not going to go into that, but you will basically create one device driver for each physical device that you have on the system. And that's how it works with keyboards. So you put a keyboard on, the one it's already on the laptop in this case, and you will have basically one driver, which is the KBD class in this case. By the way, this is just one way to do it. There's a million different ways. Usually, the lower level you go, the more complicated it gets to implement, but the more stealthy you are as well, because it gets harder for you, any blue team to pick it up, or antivirus or whatever. But so you will have one driver, which will create a device for the keyboard and put it on top of that keyboard. And it basically, for each device, you will have a device stack. And that's how you want to you want to attach to that device as well, and put your own devices there, your malicious from your created by your malicious driver that will create its own devices and put that on top of those. So you can see it here in a normal system, normal session. The driver KBD class, and then you have the driver, which will point to the first device object that it created. And if it keeps creating them, basically the way it goes is the next device from the actual device that it first pointed will point to it. And at the end, you'll have null. So it's basically a single linked list. Sorry about that. And in this case, I only have one device, one keyboard, so that's the only one you'll see there, and the next device, there's nothing. So, and this is the device stack. So you can see the keyboard class has nothing on top of it, which is where I want to put my keylogger in order to kind of intercept what is called the input-output request packet. So the way it works is when you press a key, oversimplification, because when you press a key, it's actually a key down and then an event for key up, but let's simplify it. When you press a key, there's an interrupt. Again, it goes to that URL, to the device that your keyboard is assigned, and it basically says, tells the operating system, hey, keyboard was pressed, go fetch it. And the operating system will then create an input-output request packet that will go through that device stack, will go down, grab that key that was pressed, and then return back up. I want to catch it on its way up in order to see what it has. And you can be more creative and not just do a keylogger, but you can do annoying stuff like if I press A, it changes it to B, so the person is there like, what's going on? But that's not stealthy, but just to show you how creative you can get. So that's the device stack. Now, after you do the RDP connection, you will see that now the driver points to its first device object, and that device object in the middle now doesn't have null in its next device. It actually points to another one. So you basically have one device for device driver, a logical one, for each physical keyboard that is created. In this case, the remote desktop session is seen as another keyboard that is coming virtually. So if you just attach to the first one, you won't see all the other, which is usually the physical one associated to the hardware. Now, you won't see all the RDP connections that come in, which is, you could argue, is the most important part, because if you're doing this on a compromised server, usually the admins will not actually go there physically, and they will just remote desktop into it. And on this one, on the normal RDP session, I just want to show you, on the right side, I have the keylogger already attached to it, and I just go until the second one, where you can see that the attached device is null, but on the next one, because I already attached to it, you'll see that the attached device is actually a device that was created by my keylogger driver. And you can study the differences also in the device stack. So before you had only 3 nodes in the device stack, whereas now you have 4 because the top one is the top keylogger that I just attached to it. So now I'm in a position to intercept all the input-output request packets. Let's see that happening. So here I will call, and now I have 2 more options, enable and disable keylogger, and I will set up, if I write test, you will see there keylogger1, test, showing up. Then I will access this, I'm accessing the same user, so it will drop you on the same session, but that's not relevant. It will still create a new one and a new device, and now if I type whatever in whatever desktop I'm at that session, it will still show it there. I have a small bug with the counter, but I'll fix that later. Okay. So let's talk about now, because I made a few friends in the blue team, so I always like to do it. So, reversing rootkits, why? A few important reasons, not so much the first one, but the first one is obvious. You need to be able to debug your own code. That's usually a very important skill to have. But also when debug actual rootkit malware that is out there, if you're in a red team, what you want to do is be aware of techniques that are used out there, because maybe your client wants to do a simulation of a specific attack, and you might need to understand what happened in order to replicate it. But not only that, but you can actually improve on the technique and make it better, so why not? For the blue teams, an important question to make is how advanced is an attack? And that's something that you will, often the priority is in what has happened. But you could argue that how it happened is also very important, how they did it, because there's value in understanding how good, and in trying to assess how good, technically speaking, a team that attacked you is. If they're using basic out-of-the-box interpreters and Mimi drives and whatnot, you can be quite confident that they're not going to do anything very magical in a sense. Whereas if I see them doing new techniques and using rootkits that I've never seen before and using, again, techniques that are very advanced and very stealthy, I will be very suspicious and try to analyze everything in more detail. So there's definitely value in understanding how advanced is an attack. Also for red team's researchers, debugging rootkits, the techniques to do it will overlap a lot with actually doing bug hunting in kernels, in the kernel drivers. So the techniques are pretty much the same. So if you want to do this kind of stuff, you probably want to understand reversing. So let's talk about reversing static analysis. So the first thing you want to do is try to identify the driver entry, and that's the corresponding main function from in the driver world. So the driver will get loaded, and the first part of the code that gets executed that you control as the developer, being malicious or a red team, is the driver entry. So you want to identify that and understand what is being done there. Usually device objects are created, and you want to grab the names because usually the names are how the user mode will communicate with those kernel devices, and try to see if it has stuff like device extensions, and usually that will give you you will have to reverse engineer it, and you understanding that will give you very good insight into what that device's purpose is. ERP dispatch handlers, find your ioctls. ERP dispatch handlers are the handlers that deal with the input-output request packets. So that's usually very good insight as well into what is going on. Finding all ioctl codes. Ioctl codes are, for example, are ways for you to communicate from user mode to kernel mode. Now, for example, the executable that you saw me running there, controlling my rootkit, is basically sending device IO something, I forgot now, but it's sending the ioctl codes, and those get telling, and then a buffer that can be very generic, could be anything. So the rootkit doesn't really know what's that buffer. Is it a process ID? Is it a name of a process? What is it? So the ioctl will send a code that will tell the rootkit exactly how to interpret the data that is being sent. So again, you can understand the communication because usually you will not hard code like hide process 5555. You obviously want to have some flexibility there, so usually when you're doing these kind of attacks, you will have processes in user mode that will control the rootkit, and it's important for you to understand that so you can manipulate it, if you will, or just remove it. If it attaches to any devices, my Keylogger, for example, does. In my rootkit, I actually create another driver already inside the kernel, and that will create the devices that will attach to all the physical keyboard devices. And then you want to find all the timers, completion routines, callbacks, system threads, DPCs, work items, and just make sense of it all. This slide I'm not going to talk much about because I created, because I wouldn't have time to go into much detail, but that's why I wrote a blog post a few days ago. So if you guys are interested in just very technical stuff, like loading a kernel and putting a breakpoint on its driver entry kind of thing, it's very easy on the first two ones because the first one you have to have access to the source code, so you just put that debug break where you want to stop. And the second one, you need to have the symbol file. Obviously, that's very unrealistic if you're actually analyzing actual malware. But the third one is actually relevant. So if you want to see exactly how to do it, and by the way, a side note, all of the demos are done in Windows 10, but it should work just the same on Windows 11. And but because I've recorded them like a month or some ago, and I've been through a transition period where I'm moving everything to a new laptop. And on my new laptop, I'm updating all the labs, so it's Windows 11 now on the laptop, on the labs, and the blog post actually is on that new environment, so it will be on Windows 11, talking details of that. Now, some realistic impact of modern rootkits. Now, normally, usually, what you'll have is this environment where you have the user mode and then the kernel mode. So if you get to the kernel mode, as you can do anything kind of thing. But what Microsoft did was create this whole thing that I think it's just referenced to as isolated user mode, where it created, it's all called like virtual secure mode. And the virtual secure mode basically splits this environment into normal mode, which is the virtual trusted level, that's VTL 0, and then the secure mode, which is VTL 1. This might seem like an implementation of two virtual machines. It's not. The reason for that is that secure kernel is actually not a full-fledged kernel. It acts as a proxy, mostly, to the actual normal kernel. Now, obviously, if it just did that, it wouldn't be secure. So it has to have some implementations. But just a quick note on the hypervisor. The hypervisor implements virtual secure mode using SLAT, that's second level address translation. So usually you'll have address translation from virtual address to physical address. That's in the context of the operating system. That's that gray box. But then that's not actually the physical address. There still is a translation from that address to the actual physical address. So the name it's called, that physical address is, I think, GPA, guest physical address, and it's translated into SPA, which is system physical address. And that's all controlled by SLAT. So it allows the hypervisor to basically remove visibility or permissions, whatever it is, execute, right, from the normal kernel mode. So the normal kernel mode won't even know that virtual address 10 doesn't even exist for it. So that's the power that hypervisor has. Now, there's also something called direct memory access, which is a feature, I think, that the graphic cards will have, that they can access directly the memory. That's, I think, for efficiency purposes, gaming and everything. But you don't want that feature abused. So the hypervisor will also control DMA through IOMMU. Now, talking about the features of the secure kernel, because I said, obviously, it has to implement a few things in order to be secure. So it will implement the memory manager, for example, and that's because one typical thing that happens is you want to page out the memory pages in your memory, but those in secure mode might contain sensitive information. So what it does is it has to encrypt it before sending it to the normal kernel mode that still does all the resource management. There are other things like synchronization, because there's an interesting class of bugs that you can manipulate the process, the secure process, by manipulating synchronization. So imagine like you have a rule, a synchronization mechanism that only allows one thread at a time to get into a specific area. You can manipulate that synchronization and make it believe, that thread is already out, so let another one in. So now that two are in, it can create bugs. Then obviously crypto and also marshalling, because you can't just blindly proxy stuff into the unsecure kernel mode. You have to do some sort of input-output validation, and make sure that everything that comes in and out is safe. Just quickly, things that typically will run there are LSA ISO, credential guard, that keeps most of the domain credentials, like NTLM hashes, and also virtual TPMs to allow virtual machines to have BitLocker in them. However, this is not always implemented, of course. I think last time I checked, this was only an enterprise feature. So it's not like it's all over the place, so you can't do rootkits anymore. Just some references to future work that I'm jumping into now, because I want to add stealthiness, but not only to file system, but to networking as well. And as you might imagine, that's a very cool feature to have in a rootkit. Just some quick references as well. These are some amazing books if you want to learn this stuff. For blue teams, absolutely practical reverse engineering from Bruce Dang. He's just amazing. And the classical rootkit books. And the reason I have, you might be asking, why do I have a really, really old-looking book in there? The reason for that is, as the great Dave Cutler said, there is nothing that's not NT. Windows 10 is NT, and obviously Windows 11 would apply as well. And if you're wondering who this guy is, he is one of a kind. He's the only person who's been an architect in 3 commercially successful operating systems. That's RSX 11 VMS, which was the first operating system with virtual memory in 32 bits, and obviously Windows NT. So super recommend these videos. They're long, but they're super easy to go through. And obviously Channel 9. I couldn't find the original link to Channel 9. I'm not sure if they removed it or whatever, but I found this on GitHub. And if you want the videos, you can also ask me for those. And that's pretty much it for me. Hope I made it 45 minutes. Thank you.
Thank you.
Oh,
thank you very much, Andre.
Thank you very much.
I warned you we were going deep into the kernel. and so we did.
I have to cut a lot of slides to make it to 45 minutes.
That was the simplified version, folks.
Absolutely.
So, very impressive stuff. Thank you, Andre.
You very much.
You said blue screen so many times. The next time I see a blue screen, I'm going to remember your voice and realize, oh no, I'm infected by a rootkit.
Actually, blue screens are often seen as a bad thing, but, and I know a lot of people don't agree, but it's actually a protection mechanism, because if something is going wrong in the kernel, you don't want it to keep going. So the operating system self-protection is just, let's just stop this right now. So look at blue screens in a different way next time.
If it's a good thing, why does it have a sad face?
No comment.
Okay. Any questions for Andre, folks? All right. Just make sure I'm not missing any hands. No. I have a question, because your title is Red Team, and you talked about reversing as well. And it seems like you're quite into this from the development side of things and actually building these tools. In your work, is it more on the offensive side? Does the average client that you're seeing, and this may be different in the different countries that places you've worked in and so on, but was the average client, is it more likely that they're going to get value out of a consultant deploying custom rootkits, or are you more often called in to investigate something that's found inside a client network from a forensic perspective?
I think it's important to note that a lot of people will try to make a very clear split between red team and blue team, but I don't actually see it that way, because a skill that is often associated with blue teams is reverse engineering skills. And if you ask me, like, that's probably the thing I'm best at, but I'm at a red team. And the reason for that is you need those skills in order to understand the security controls that are thrown at you and in order for you to bypass those. So kind of mixing them both, obviously you won't see me out there like installing firewalls or other stuff like doing cloud or anything, but I need to go really deep and understand how a security feature will work so that I can understand how to bypass it. So often you will hear me talk about security protections because I understand them so much, not because I'm out there in clients implementing them, but because I had to reverse engineer it and understand like really how it works in internals, and so that then you can work doing exploitation or whatnot to circumvent those. So it's definitely something I would absolutely, if it's not being valued out there, it's being done wrong. So yeah, that's it.
Cool, thanks for that. So it sounds like purple team then. Yeah, you heard it here first, folks. Any questions before we? Anybody? It's a little hard to see at the back.
I'll be around anyway,
yeah.
so.
Yeah, find Andre and ask him any questions you have. It's a great opportunity. Otherwise, we have lunch.